started with this a property of invertibility, right, in the case of matrices, right? And then we went on to try to generalize and try to look at some variations and see connections with nilpotency and when local.
Yes, sir. Can you hear me?
Yes. Right. So let me just state the result that we have proved and ask you if you have understood it. Okay. And then the further things which we are investigating. What have we proved? So we have proved the following. There are two operations and they have their identities. Each of the operations have their respective identities. And the condition is that every element is either nilpotent or invertible. Okay. And so you can imagine that S is some collection of matrices. Okay. S is some collection of matrices. Okay. Giving an example of such a collection, I can do that. But let me not do it at the moment. Okay. We can do it, but we will do it a little later. But it's like this is a condition. And then we showed that this implies that U and V in S such that UV invertible. Okay. This implies that U and V are invertible. So is there any problem with understanding this proof? Fine. Right. So we basically looked at the smallest nilpotency and we did that degree of at which it becomes zero. It is important. Okay. So now I will say a few things and I'll strictly leave them for homework because we should move on to other things. Okay. Yeah. So Rohan, is all this okay so far?
Yes, sir.
Okay. Right. So the homework number 1 would be that assume. So well, you should know that whenever I write plus is commutative. Okay. Addition is commutative always, meaning that the one of the operations we assume to be commutative and we denote it by addition, just like in matrices, integers. And multiplication is not given to be commutative, so I'll not say anything. And it's associative and everything I'm not writing. Those things I'm not. Yeah. This is called a ring. You should know it. If you don't know it, read the definition. Assume assume now that this is commutative. Okay. And show that U and V nilpotent imply U plus V nilpotent. Okay. And second is show without commutativity. And this will also be true without commutativity, but proof might be, I don't know, easier after that. So the same without any assumption, without commutativity. These are two homeworks. Again, similar ideas you have to combine all the mixed ideas. So also earlier we did, right? this kind of question, that if A is nilpotent and this is identity, then this is invertible. You remember? That was one of the Artin questions. That will also come into play, I think, depending on how you prove it. So everything, so it becomes an interesting question, I think. Now I want you to uh, do an example of this kind of thing. So see if I can say. So yeah, does everybody understand what is Z mod NZ? In whatever way you understand, you can tell me. Rohan, what does this mean for you? Z mod NZ? Anything if it means.
Z. Once again, sir. Can you? What does it Z mod N means?
Yes, yes. So basically, you can think of it as, so everybody can think of, if you know proper definition, it's fine, but you don't need it for this problem. You just think of it as the integers from 0 to n, and addition and multiplication is done modulo n. That is
Modulo
fine.
N.
Modulo n. That is fine with everyone.
Right.
Yes, sir.
Arnav, is that fine?
Yes, sir.
Right. So you probably already know what Z mod NZ means as a
Yes, sir.
ring. So yeah. So yeah. Okay. So okay. Now you do this problem then. So right. Show so that Z mod NZ. So Z mod NZ has the addition, multiplication, all these things it has. So it is a structure like that. It is a ring. Or you can just, to work with it, we use all those rules which we have. Rules, Artin, mod, and show that this satisfies this star, has this property, if and only if, any guess? N is what type? Power of P, a power of prime. Prime will work, but also any prime power will work. And only those will work. I mean, if it's prime, then there are no nilpotents at all. Then it's a field. Then everything is invertible. Right. Every element has an inverse. Right. A mod n, mod P. But if it's prime power, then that's a generalization. And that's this kind of. So, and if and only if. Condition is very nice. You will use it. But this is a rather trivial example. More interesting example should do. So two levels I want to do more. So one example would be slightly more difficult and one would be more difficult. But all these you can just do with scratch. That's the good. Right. So you look at this kind of matrix. Okay. Maybe you can take 4 by 4 or 3 by 3, doesn't matter. Or you can take 4 by 4. So that you can, if you can do this without calculations, it will be better. That's my point. So you look at this. Call this J lambda. Okay. And now you obviously this is just a point. It's just one matrix. This doesn't do our problem job. We want to create a ring out of this matrix. So how do you do that? So you look at this set. The set S that you form will be P times J lambda, where P is a polynomial. Okay. Right. So it's like J lambda square, J lambda cube, J lambda square plus J lambda cube, and things like that. Okay. P is just a polynomial in one variable. This. Let's show S has the property star. And lambda is anything. I am not saying anything about it. There is one more, let me say, it will be more abstract. But yeah, but this you can do workout. If you cannot do the 2x2 or 3x3 case. You can already see that this lambda is 0 means it's nilpotent, and lambda is not 0 means it's invertible. So already the start is already there. The kick is already there. You have to just show that anything you generate from it also has the same property. Right. Now let's make it more interesting. Okay. So again, you can take n to be 3, 2, whatever is up to you. But I'll say it for n because this is supposed to be a difficult problem. Difficult means it depends on your understanding. I'm just thinking if one can go and try to make examples of such things. Let's say that A and B are in M and R. Okay. And as I said, you can take M equal to 2. A and B are in M and R, okay, such that no, wait 1 second. B, and you take this, and then you take the center, and there whatever works, E, right, probably it will actually be more, but you prove it. Let's see. So A and B are in M and R, okay, and then you look at this S, or actually I should not call it S. I should let's call this. Wanted to call it anyways. Let's call it R. So the different R. Okay. This R is again just polynomials. Okay? 2 variable. So Px comma y. It's 2 variable polynomials. Okay. Now R has a very interesting property. Okay. What is the property? Given any 2 vectors, so for all given any 2 vectors in Rn, probably this becomes a little, it's not difficult, but just that it's bad language in which I'm writing, so it looks very long. Okay. But yeah, maybe forgive me for this. So V comma W is in Rn, but I just want to say it to fit the whole picture. V comma W is in Rn. For all, if V comma W you take in Rn, then there exists. Okay, there exists. There exists a T in R. Maybe this R can be a family R like this. Okay, this R such that this is a matrix, right? T will a matrix such that T takes V to W. So this family is sort of nice, right? Any 2 vectors, if we call one guy from there, take V to W, that this vector or that vector. Okay. Right. So this is this, and now you take center of R. Center of R, what I mean is basically you take, it's just a definition, you take all those U such that U comma T sorry, u times t is equal to t times u for all t in R. Okay, so now I'm taking a different thing. I'm taking those things which commute with everything. So some commutativity getting some commutativity. Okay, and then the question is again, show that this ZR has addition multiplication, means that if two things are in ZR, then sum is there, product is there, and so on. Show that ZR satisfies star. And everything before that is a special case of this. At least, yeah, at least 4 is a special case. Satisfies star. Okay. So these are the things that you should try. At least first 4 you should do. So this, in a way, this characterizes all the, what I'm trying to get at the end is all the important rings which satisfy this property we are trying to characterize. And matrices don't satisfy this actually, but they also have this property. Matrices don't satisfy this, right? But they all matrices don't satisfy this, but they also have this property. But actually, what we do is we take any matrix and we will say later is there is a way to break a matrix, a proper way to break a matrix into pieces such that each piece will satisfy this. And that is where the theory is headed. When you go to the last page of the linear algebra portion in Artin, this is what they will prove, Jordan canonical form. We will talk about it later. That is, so the theory goes to breaking every matrix into blocks which satisfy this. Okay, so you see, so basically everything that satisfies this property is either of yes, everything that satisfies this property, meaning that UV invertible implies U or V invertible, is either this kind, which is means every element in it is either nil. Every element in the thing you generate by adding and multiplying the things, okay, of that kind, which is the S that you generate, will satisfy this property, or that S will break up into things which will satisfy this property. That is what we want to do. It's called fundamental theorem of modules over principal ideal domains. So, yeah, that is what it says. Cyclic modules. Yeah, we could say that. Yes. Okay, so now let us move on. Okay. We'll go till 10. I'm saying this extra thing, so you try to work with time to it. But these problems are all easy, okay? They are not. So what should we do next? One problem from Artin. Should we do the next problem or should we do something that I gave last time? Let's do the next question. Let's do the next question. Actually, these are already subsumed in what I had given last time, but anyways. So let's take 2.9 and see what it has. So consider an arbitrary system and so should we do 2.9 or like any suggestions? No? Yes. I don't know. Has anyone done 2.9? Wait, what happened? I cannot hear anyone.
No, sir. Actually, in the background, I was trying the second question that you just gave, and I
Okay.
have a doubt in it. I
Okay.
think it's in the last slide.
Okay.
Yeah, yes, sir. Oh, sorry, third question.
This one.
Yeah, yes, sir. So, what I did was I just took an element which has an inverse, say A, and A into A inverse is equal to E.
Right. Okay.
And so I'm assuming it's invertible. Then what I can do is for any natural number.
Yeah, but what's the doubt?
A,
Because otherwise everyone will get
so
the
the
solution.
doubt is I haven't used the prime power condition, so I don't know where.
No, you have to use the prime power condition. Okay, otherwise you'll get some counterexample, right? So if you take Z mod Z6, 6 whatever, 6Z,
Yes.
right? Then you look at element 2, right? It is not nilpotent and it is not invertible.
Okay.
So you will need
Yes. Yes.
to think. I mean,
Good.
yeah, do it at a peacefully later. So let's do 2.9. 2.9. You will need if and only if the question is correct. If, it might be wrong also because I'm making all this, just saying all this just now. Okay, so final, I'm asking, what should we do next? Come on, it's not anything. Arnav, what's your suggestion? I think Rohan was not there in the last class, so probably doesn't have an opinion now.
No suggestions.
Sorry,
No suggestions right now, sir.
no suggestions? Okay, all right. So then let's do the next one. Okay, so when we say arbitrary, then it's yeah. So let's take n. So A becomes a n by m matrix, right? So n rows and m columns. I'm taking it like that because when this is system of equations, then I think it should be like that. And what should be the dimension of x and b? That everybody should know. What should be the dimension of x and b? If it's a system of equations, right?
So X should be a column. So M cross 1.
Yes, right. M cross 1, correct. And what should b be?
So N cross.
And n cross 1.
N cross 1, right? Perfect. Did I write correctly? Yes, that's correct. Okay. So this is what they are given. And last day, I think, I don't know who was there, but I had asked a full set of questions on this, and that subsumes this. So they're saying, okay, prove that if the system has one solution, more than one solution, then it has infinitely many. So right. So how do you do it? So assume more than one solutions. Assume that um, let's say that x and y are two solutions, right? So how do you produce more solutions? So you can also just write a 2 by 2 case, right? Get some inspiration like this. Just some b1. So if this system has two solutions, then why are there infinitely many solutions? Okay. So this may not be helpful, but can you think of a reason only for this? I just want that system has two solutions, and why are there infinitely many solutions?
For infinitely many solutions, I guess that would be A11 by A21 equal to A12 by A22 equal to B1 by B2. Something like that.
Uh, okay. So you're using some condition, Right, correct. Yeah. So, so what was the, so there was some condition, yeah. But yeah, that condition is there, but basically you can just, yeah, this same thing. Basically, this particular thing is what? It is just, so the first one is a line, right? It's a line. Second one is also a line. So this is a typical condition case in which the lines meet at one point, right? But if there are two solutions, it means that the lines meet at 2 points. Agree? Right? Yeah. If this has two
Yes, sir.
solutions, it means that the lines meet at 2 points. Solutions means what? X1 comma x2, which satisfies both, which means it's on both the lines, right? A point in the plane which is on both the lines. If there are two such points, it means that all the points on the line are same, the lines are same. So that means infinitely many, right? But I don't know, maybe that doesn't help to solve the n by n case. So how do you do it? So let's write it and see if it gives us something. So it is this. So there are two things which satisfy it. Can you give me more things that satisfy it? Come on, be creative, right? Just give me one more thing that satisfies this. Convex combinations? No, no. We'll do it. You can do it from the theory you have studied, but you can also do it. You don't have to apply the theory for everything. Any lambda, any scalar lambda? Agree or not? Just add the equations. Multiply 1 by lambda, 1 by 1 minus lambda, and add it.
Yeah, okay.
Okay, right? So this is the thing. And this is not really magic, right? I mean, if so I mean, you can imagine there are two planes or lines. If you're still not comfortable with it, it's a different thing. But right, the two, like these are two straight things, right? If they're cutting and if they're meeting at 2 points, then all the points that are on the segment joining will also be solutions. That's geometrically it should be true, and algebra just confirms, or yeah, whatever one wants to say. It's true, but I don't know. Yeah, this is one way. But you see, last time I had said something, and from there also it follows. So let's do everything then. Is there something? Yeah, eventually you would want to say that the solution set is a coset. Is a coset of something, and if the coset, all cosets have cardinality same, and the coset at b equal to 0 has cardinality infinite. Is a vector space which either infinite or filter. But yeah, probably you don't want to use cosets yet. But so let's see. We have spent a lot of time studying the homogeneous version, so we will want to solve this using that. Right. So if this is one solution, and let's say y is a solution, another solution, then can you produce a solution for this equal to 0? Yeah, so that's a very clear question. Can you produce a solution for this a times something equal to 0? Can you give me a something there? Anyone? You have two solutions, same system, but you have two solutions. Now you want to find a solution for equal to 0.
So x minus b a inverse.
No, there is no inverse here. You can just do x minus 5. You don't need it.
Okay, like that.
Yes, x minus. Yeah. Everyone fine? You get a solution, right? Non-trivial solution, x is not equal to y. This is what I was saying last day. So the formula you get from here is, so let's just call this thing z. Okay? And what is y? Y, or what is x? X is equal to y plus z. Okay? So this is what I was saying last day. And you should remember this. Okay? This is very important. If y naught is a particular solution, and you would have seen this kind of statement in differential equations and so on also, or you will see, is a particular solution of a y naught, is a particular solution of this. I should write ax equal to b because then I'm saying of, so, but if is a particular solution of this, it's actually pedantically, if you want, it should be actually ax solution of what equation. If I write this, then it's no more asking for a solution, it already has it. But anyway, you understand. So if y naught is something that satisfies this, okay, then this collection y naught plus z, okay, where az equal to 0, this is equal to, this is all the solutions, okay? All solutions of this equation ax. That's what we have shown right now, right? Any other solution, x was a random solution, right? Any other solution x is nothing but one solution. So you can take any one, fix one solution, guess one solution, right? And then add the solutions of az equal to 0 or ax equal to 0. Right? Add the solution for the 0 case. Fine. Arnav, this was one of the homeworks, right? Is it done now? Is it fine?
Yes, sir.
Yeah, I understand. I mean, these notations we are not used to using. That's the only. Otherwise, if you just sit back and think it's all easy, but you have to get used to it. Okay? So all the solutions come like this. Okay. So what does this mean? Let's try to investigate this. What is the further conclusion? Further conclusion. This means that if you look at this solution set of z such that az equal to 0, and if you look at this solution set, maybe I should use a different notation. Otherwise, a is same, obviously, I mean, just to say. Then these two sets have the same size. They may be infinite, but there is a very clear bijection, right? There is a bijection, right, between the solutions. That's what this theorem is saying. So how is the bijection coming? Bijection is like you take y,
So you can send y to
or maybe from
x.
this same thing.
Yeah.
You can send this to y naught plus z, where you fix y naught once and for all. Right? Fix y naught initially here, and then you obviously provided that there is a solution. Provided that there is a solution, otherwise don't blame me. If you do not find this y naught, then this may not have any solution. That also we have seen, and this may have infinitely many solutions. Right? Fine, right? Yeah. Having one solution to start with is important. Otherwise, it obviously doesn't work, and it doesn't work when it obviously doesn't work. So it's not a problem. Nothing that you have to remember deeply. I remember very right in front all the time. Right? It's there. It's a bijection. Correct? So we are using these different ways to argue, remember. I'm not going by the same old thing and reasoning it. Okay, or just showing one trick. No, we are reasoning it through some interesting ideas. So there is a bijection. Okay. So if you want to show that this set has infinitely many solutions, you can reduce the question to this has infinitely many solutions. Welcome home. This is the what we already have talked about. Correct? Right? You already know it has two solutions. Two solutions for this means that this has at least two. At least two for this means at least two for this. It means there two may be x and y are solutions is at least two. It means this is also at least two. Correct? But these solutions obviously form a vector space, right? Because what do I mean? This is obviously right. If x is a solution, then lambda x is a solution. This for zero, it's not a problem. Zero is like a singularity, right? It follows everything. So obviously there are infinitely many solutions because our field has infinitely many elements. R has infinitely many elements. Obviously this solution, if x is a solution, y is a solution, x plus y is a solution. So in that case, it's obviously if it is more than one. It's either only one or it's infinite. Okay. And we have even done more, but this reasoning is sort of bypasses it bypasses solving the solution system completely. Not a trick. It's not a trick. It's a nice way. But you bypass. You only do what's needed. Right? We are not getting into dimension of solution and so on. No knowledge of dimension is needed or anything, or explicit form of solution, or matrix is not invertible, or not using anything directly. But this you must see. This is a very important lemma. Maybe Artin doesn't write it, but it's important. All the solutions are given by translation, but that translation must exist, which means there must exist at least one solution. So to summarize, this is the most important result we have seen. It's easy, very easy, but it's important. So this is what we have learned today. Second topic. First topic is about manipulation. Basically, some manipulation. There is also some symbolic manipulation. The good idea here is this. I would is that size is same, because you see size is same, and therefore to show one thing is infinite, you use the fact that the other thing is infinite. But the other thing has a structure, right? The other thing is like if one thing is a solution, that sum is a solution, and a scalar multiple, you can use that structure, and that structure is well known. That convex combination maybe was a trick or the new thing, but this has a solution as a structure everybody knows. If x is a solution, y then x plus y is a solution, and so on. Okay. It means it's infinitely many. But the job of linear algebra is really to understand that infinity. That whether that infinity is one-dimensional infinity or two-dimensional or three-dimensional, which one talks about later. So yeah, let us stop here and then we'll meet on Sunday, 8:30. Please continue to section 3 and other problems I've asked you. If you have any further things, you can ask me, mail me, or call me also if I there. I'll try to reply. Okay.
Yes, sir.
See you then.
Yes.
It's going to end, so stop.
Yes. Thank you,
Good
sir.
night. Good night.